So Catalog as a company is addressing a huge market that's all of sort of parallel computation. We see that as a $100 billion market, but as a first step in getting there, we're tackling the cold tier archival storage market. That's about at 7 to 8 billion right now. So as we develop technologies to do more computation and improve the read and write characteristics, I think we'll be in a really great position to get a large portion of that much bigger, broader market that's out there. And so in terms of the fundraising, we have great venture capital firms that's already on the cap table. And on the milestones that we'll be meeting in the next few months, the completion of a terabit machine and having some pilot customers on board, we'll be going out and raising another round, our Series A round, during the first half of this year. So I think when you think about the process of storing information in DNA, you really have to start from the very beginning. What does it actually mean to store data? You know, maybe it's a file of a picture, a JPEG, or a text that you want to store in DNA. So for us, that's no matter what kind of data it is, it's just reduced down to a series of ones and zeros, a bit stream, binary data. So how do we turn those ones and zeros into the physical presence or absence of these DNA molecules? Right, so in between that sits a computer that uses our codec to read the binary information and generates instructions for our liquid handler to move around our pre-made DNA oligos and combine them in combinations that represents the ones and zeros that we want to store. So we would take the bits, turn them into instructions for the machine would go in, move around DNA molecules, combines them into the pools that represents the ones and zeros that we want to store. And then in the other end, the machine would collect all of those DNA molecules and pool them and concentrate it down to a pellet. And when we want to restore and retrieve information from it, we would put those DNA molecules into a sequencer. And these sequencers are not any different from the ones you would use for genomic sequencing. And so we can work with any genomic sequencer out there or any DNA sequencer out there right now. And at any given point, we would work with the platform that gives us the highest throughput for the lowest price. And in reading back the information, there's also an issue of error correction and detection, because reading back DNA molecules isn't a perfect process. It's a random sampling process, and in the samples that you're reading back, you also get base pair errors. So that's less of a problem for us than it is for diagnostics and therapeutics, because we're using large chunks of DNA molecules. And the problem of calling whether these larger chunks are there or not is a much easier problem to solve on the sequencing side than going down to the base pair resolution and trying to read every single base pair.